So question 1, we have a resistor capacitor circuit with a varying DC input being made more steady using a capacitor as shown. So quick look at the circuit. Voltage being measured here across the capacitor, so that would be VC. You've got a load resistance of some sort, and you've got an input signal which is your varying voltage which your capacitor will be smoothing. A is calculate the time constant tau for the circuit shown in which the capacitor has a value of 1.2 times 10 to the minus 7 microfarads and the resistor is 1.0 times 10 to the 3 ohms, which is 1 kilo ohm. So remember, the time constant is the resistance times the capacitance. So in this case we just multiply these two together and we end up with 0.12 to 2SF, because everything's 2SF, and it's milliseconds. Small m, small s, milliseconds, 0.12 milliseconds. We've got the input signal varying as shown here. I'm going to describe how the voltage across the capacitor changes between the time of 2.2, which is just there, and 3.0, which is there. Your answer should include a sketch on the graph on the opposite page, which is meant to be the graph above here that we're talking about. So it's the graph above. Okay, so let's just go back up to the circuit. When the input, presumably the input signal varies from a maximum to 0, and it's shifting back and forward between those two. You might like to think of it like this, and then it goes across at 0 and back up, and something like that. When it's at maximum and it's at a steady state, there is no current flowing through our resistor over here, which means that the maximum will be the voltage across the capacitor. Those will be the same. As it's charging up, there's a small voltage drop across the resistance, or there is a voltage drop across the resistance, and a voltage drop across the capacitor. And then once it reaches 0 volts on a discharge, it's going to also have 0 across the capacitor. In any case, B, describe how, so we've already talked about the question, we're trying to describe how the voltage changes between these very specific times. So this is at the falling edge of DC signal. So we know the time constant is 0.12 seconds. So on this graph, that would be roughly a little over 1 square in length, because that's about 0.1. Each square is around about 0.1. So instead of it dropping straight down as the graph appears to show, a little bit over that, it's going to drop about 63%, which will be about just over 12 or 13 volts, down to about 7 after about, so it's going to be around about here. That's roughly where it's going, and then it's going to drop about the same proportion, 63%, after another 1.2 seconds, so around about here. So that's going to kind of come down like this. Whoops, I've drawn that poorly, and then it's going to just keep, not quite touch there, but yeah. So that's the visual of what's going on. If you were to describe how it's changing, you would say, talk about the time constant being 0.12 seconds, and you would say that between from the 2.2 seconds to 2.32, there would be a drop of 63% of the available, and then so that's 2.2 to 2.32, so that's one time constant, and then you would say from 2.32 to 2.44 there's a drop of another 63% of whatever's remaining. Has to be of whatever's remaining, remember, and then again it would drop the same, and you sketch that roughly. Okay, C, calculate the charge stored on the capacitor, 0.24 milliseconds after the input voltage drops to 0, so that's 2 time constants. That means we're going from 100%, one time constant takes us to 37%, which is 0.37 as a decimal, and then we go down to 37% of 37%, so that would be 0.37 times 0.37. That will give us the actual decimal value of it, which is 37% of 37%. If you like, okay, you can follow that. So you have to calculate the charge first, stored on the capacitor fully, and then multiply it by 0.37 twice. So Q times by 0.37 times 0.37. I'll just go and grab those numbers and perform the calculation. So Q equals C times V, which we had the capacitance up there, I think, what was it? I've forgotten, totally forgotten. Way up the top. There we go, 1.2 times 10 to the minus 7 farads. And the voltage we can get from the graph is 20 volts. So 1.2 times 10 to the minus 7 times 10 to the minus 7. I usually put those in brackets because it helps me think about those. Times by 20 volts times by 0.37 times by 0.37. You can put that in your calculator and work it out. I don't think we need it for any further questions. D. Explain why an RC circuit, this is the last one. Explain why an RC circuit like this smooths a rapidly changing input signal to less variable output voltage as shown below. So it goes from this to this when we add a capacitor in series. Okay, your explanation needs to talk about the charging and discharging characteristics of a capacitor. So it's very much the same. When it's charging, it'll take time for the voltage to build up. So it's not instant like an instant change or a fast change like we have in here. It takes time according to the time constant, and therefore it slows down the rate that it's changing by. And this means when it starts, when it goes down the other side of the slope, so we've talked about charging, when it goes down the other side, there hasn't been enough time for it to completely reach its peak or reach its minimum. So not enough time for the capacitor, the time constant, to finish charging or discharging if you're talking about the other way. So this really means that your time constant of your capacitor has to be set to match what you're trying to achieve with your charging or discharging. So there's no good having a time constant. Say if this is your signal and you're trying to reach this, there's no point having a time constant that is about 1,000th of 1 division on the scale, because it's not going to have enough of an effect. That means the capacitor would reach its charging and you would have exactly the same graph down here. It would reach its point quick enough. If your time constant is, say, the same length of time as here for it to change, then it's going to have a much greater effect because it's going to resist change essentially. Anyway, I think you get the idea. That's that.